All right, variable forces number 2, we're going to apply Newton's second law of motion. That's what our learning goal is. We're going to build on what we learned previously, and we're going to look at how we can deal with forces using Newton's second. And just to recap previously, these 4 expressions for variable acceleration based on what we've been given and the initial conditions. Okay, so that's in the previous video. And the last 2, well, some people argue you don't need the last one. That's technically true, but it can be handy. Okay, so the last 2 can do swapsies sometimes, but if you're given a as a function of x, as we'll see in the second example, it actually is more immediate, arguably, just to go with that expression. Okay, so the first of 2 examples here, and we are in a straight line. We're assuming, so this is one-dimensional motion, so we're going to relax the vector notation. So with vector f equals m times vector a, so Newton's second law essentially, we're just dealing with one dimension, so we don't need to get particular about vectors. But force and acceleration are vector quantities, but we're going to simplify it just down to the magnitudes. Okay. Alright, so we have some key information here. We got 5 kilos. Initially it's at rest, so that means when t equals 0, the velocity is 0. Okay, so list all of your given quantities there. We've got our quantity for force. It's f of t. Okay, so that's important as well. F as a function of t, so force is time dependent, and that's our restriction on our domain there. Find the speed of the body after 6 seconds and the distance travelled. Okay, so we've got F equals ma. Now this is the main difference between moving from the previous acceleration questions we did and the force ones. Okay, so F equals ma. Now we're given F equals, see, I'm just going without the vector notation now. We're given F equals 6 minus t all squared newtons. And F equals ma, so m is 5, so ma, 5a, equals 6 minus t all squared. So this is where we're applying Newton's second. And I talk about that law of motion in previous videos, so make sure you're watching these in the right sequence. So a equals 1/5 of 6 minus t all squared. Now we're going to use dv dt because we've got force as a function of time. And we're told about the initial velocity, so we're given v in terms of t, so we're going to go with dv dt in a question like this. Thus, dv dt is 1/5 of 6 minus t all squared. So to get v, we have to take the integral, so we can say that's 1/5 outside of the integral of 6 minus t all squared dt. Now, using integration by substitution, which is in a different video, I'm not going to show that bit, we can get an output there. So that's a u substitution, alright? So remember how to do a u substitution. That's the result of the u substitution. Now we've got the plus c on the end. We apply the initial condition, so when t equals 0, v equals 0, so subbing those values in to get our value for the arbitrary constant. Okay, so we put those in there, and that will give us, with a bit of calculation, the constant comes out as a fraction, 72 on 5, or you can use a decimal approximation there, or in fact a decimal exact value. So there's our full expression for velocity. So we were asked at t equals 6, we were asked to find the velocity, so we sub in t equals 6, and interestingly enough, we get 6 minus 6 there, which is 0. So all of that first term comes out as 0. So that means velocity is 72 over 5 meters per second. Now we had to find the displacement, or in fact it was the distance that was asked for. So x, we have to integrate the expression above there, that one, and I'll leave you to do the u substitution there, because that's another u substitution using the same process. So we're going to integrate this with regards to t, and to save some time you should get the following. Okay, and I've used plus d because we've already used plus c for a different arbitrary constant. Okay, so initial conditions, t equals 0. It starts at the origin, alright, and that's what the origin is, and it's place of origin, so at t equals 0, x equals 0, so that gives us, you'll find that we sub that in, that gives us a d value of 21.6. Try the full calculation yourself, pause the video and try it. So that means at this t equals 6 that we have to find the answer to. We have a substitution to do. So x will equal 72 over 5 by 6 minus 21.6. So 72, so that's a positive 6, by the way. It looks like a negative, it's a positive 6. Take away 21.6, and we get 64.8, and that's meters travelled. The final of two examples, we've got a particle of mass 3 units. Look, I'm just going to say it's 3 kilos, all right, and moves in a straight line at time t. I've changed the question. All right, at time t, the position relative to a fixed origin and its velocity is v, so we're using symbols x and v. And cutting to the chase here, if the resultant force is 3 plus 6x and velocity is 2, let's say meters per second, all right, keep standard units, when x equals 0 meters, find v when x equals 2 meters, okay? So let's have a look at what we got here. So F, Newton's second law, F equals ma. And because this is a straight line, all right, drop the vector notation, so we'll relax that there. So the ma part is 3a. Now we'll drop the vector. Okay, and we've got an expression 3 plus 6x. All right, so 3 plus 6x equals 3a. We've got a force in terms of x, and we're given information about x and v. So I'm going to use that one, although you could use that one as well. So I'm going to use the bottom one there, d dx of a half v squared. But you could use v dv dx as well. Just simplifying that by dividing 3 by 3, and now we can replace the a with d dx of a half v squared equals 1 plus 2x. Okay, so I'm just using a different notation for the arbitrary constant. Use c's and d's in the previous one. You could, if you've got different constants, you can call it c sub 1, c sub 2. So basically I've integrated both sides, all right, and that's no problem. I think by this stage, some people would be happy to leave it as half v squared. I'm going to leave it as v squared. Don't go for v, please. Just leave it as half v squared, or in fact v squared is fine too. So just multiplying through. I don't feel like dealing with the half. And 2 times c1, let that be equal to c2. All right, so 2c1 equals c2. And we've got an expression for v squared. Now, those initial conditions, we've got x equals 0. We have a corresponding v equals 2. All right, so v squared will be 4, and that'll be c2. Alright, so that means that we can update the expression like that there. So at x equals 2, because the question asks us to find x equals 2, when x equals 2. Alright, we look at that by substitution there, so we got v squared equals 2 by 2 plus 2 by 2 squared plus 4, and we've got 16 there. Okay, so v is plus or minus 4 meters per second. So there's two solutions, there's two velocities there, and that happens sometimes. Thank you.